So, last time we proved Janson's inequality. So recall our setup. We have a finite set, universal finite set omega. And each element of this omega belongs to this random set with certain probability. And for different R, those events of it belong to R are all independent. And let's say we have this collection of subsets AI, and Pi indicate the event that each AI belongs to this random set. And we write I and J are related if AI and AJ have a common intersection. And X counts the number of, these events happened. And we measure the dependency over these events, which is delta. And what Janson's inequality says is the probability of X equals 0 is obviously at least M, which is roughly e to the negative mu, where mu is the expectation of X, expecting number of bad events happening. Then what Janson's inequality says is that none of the bad events happen is approximately, same with e to the minus mu if this delta is small. So if delta is small, smaller than mu, much smaller than mu, we get roughly, optimal, almost optimal number on the exponent. And also, we proved the extended Janson, showing that if even if delta is bigger than mu, we can still, bound this using this expression. And we also learned that with a slight different setup. So, for example, we don't assume this independent event. So each of these element belong to this random set in an independent way that give us this measure. But we can consider some other measure which satisfy the FKG inequality, and we consider some bad events which are increasing. Then we can again define this if Pi and Pj are pairwise independent, not pairwise independent, then we write this I related to J. And we measure this, and then we consider the, probability that no bad events happen. Then the proof of Janson's inequality also works in that setting. So there, the probability measure is defined, not necessarily defined this way, but as long as we have, we know that these events are increasing event, and the measures are given to this selection of R in the way that we can apply FKG inequality. Then, this Janson's inequality work. That's what we learned last time. And using that, we estimated the probability that GMP is triangle free for pretty much all range of P. And we can actually generalize, so maybe we can recall what is actually the statement that we proved is the probability that it is triangle free is either e to the negative more or less, 1 plus root of 1 times n cube p cube over 6 if p is much smaller than 1 over square root of n, and it's more or less e to the negative theta of n square p if p is bigger than some constant times 1 over square root of n. We can also generalize the proof of this into not triangles. For example, we can prove the following. Recall that before we define that a graph H is strictly balanced if for all subgraph H prime of H, it's not dense, it's more sparse than H. So, for example, if you have a triangle, then ratio between number of edges and number of vertices is 1, which is density. And for this specific subgraph, we know that there is 1 edge and 2 vertices, so this one is small. So once you zoom into a smaller subgraph, it's always more sparse. But for example, if we have this, then this is not strictly balanced because you have 7 edges, 5 vertices. But if you just take this subgraph, then 6 edges, 4 vertices. So this doesn't satisfy. So this is because in here, this adding one more, vertex and edge is, not essential. So as long as you find this in, say, random graph, adding this one more thing is not difficult because we know that this vertex in random graph has degree at least 3, degree at least 4, that's easy. Degree at least NP, and then here P is some number which ensures we can find this, then obviously you can always add this. The real problem here is finding this in random graph. That's more difficult. So if H is not strictly balanced, then the finding H in random graph is as hard as finding H prime, which has more density than H. So we might as well focus on H prime instead of H. Because as long as we find H, then H prime, then finding H is, not much more difficult than finding H prime. So that's why we are focusing on this strictly balanced graph. So now we can prove this theorem, which generalizes the argument over here. But if we fully generalize this argument, then statement become a bit messier, and we don't gain too much from a more messier statement. We just want to consider a specific P. So here we consider, wide range of P, but here we don't want to do that. We just want to consider a specific P. So let H be a strictly balanced graph with, say, V vertices and E edges, and A automorphism. So here automorphism means that this graph and this graph, if you map this 1, 2, 3 to this vertex to, say, this one, this to this, this to this, this to this, then both of them. So while mapping the vertices, edges are mapped to edges here, edges are mapped to edges here. So you can actually find the map from vertex to vertex, so that the edges is H is also mapped to H. Then we say this is an automorphism. And it measures, how many ways to actually draw one graph on 3 vertices. Say you have these 3 vertices. Then these 3 graphs are actually same graph. So there are 3 factorial ways to map this 1, 2, 3 vertices into 3 vertices here, 3 vertices here. There are 3 factorial ways, but there are 2 automorphisms. So there are this many ways to, get undirected graph over these 3 vertices in a different way. For example, triangle is there are only one way to draw it here with this 1, 2, 3 vertices. So this is 3 factorial over 3 factorial because this triangle has 3 factorial automorphism. So that kind of measures how many, different way you can actually get the same undirected graph. No, not undirected graph. Same graph with when you forget the label. So unlabeled graph. So why did I say undirected graph? So unlabeled graph. Anyway, so in that setup, let's say C is a positive number fixed. And if we have a P, which is C times N to the negative V over E, then what we have is that for specific this function, the probability that GMP has no copy of H is more or less the exponential of minus C to the E over A plus little of 1. So we want to measure this. We want to prove this. So this is again roughly the expected number of copies of H in GNP. So this is expected number of copies because if we consider the all possible copies of H in here, these possible copies are collection of H's. So for example, if you want to find this copy, this is H, then we have what we have to do is we choose 3 vertices, say 1, 2, 3. Then either we can have this, this. So 3 n choose 3 times 3 is the number of ways to actually get it, which is n choose b times b factorial over a. So you can easily check that this is the number of ways to, all possible number of ways to get the copies of H. So for each alpha, which is between 1 and this possible number of all collection of H's forming H, we let A alpha be, range over all H sets or possible copies of H, and let B alpha be the event that this A alpha, the set of H's, belongs to the, let's do this, they are all H's in G, where G is drawn according to the distribution G and P. Then what's mu? Mu is, there are this many events B alpha. Each of them happens with a probability P to the E, because each pair belongs to the GNP with probability P in independent way, which is, if you compute it, we have roughly this C to the E over A, because we know this. And what's M? M is, again, for each P alpha, the probability that it happens is P to the E. So you multiply all the events as if they are independent. I mean, all the events that the PI doesn't happen, then again, I mean, this is, if you use this as e to the minus xn, so if you use this approximation, then this is again e to the, say, exp of negative c to the over a plus 3 log 1. So this we know. So now we want to apply Janson's inequality. So in order to apply the Janson's inequality, what do we have to do? We have to measure the dependency. How weak the dependency is can be measured by this, computing this delta, which is we consider all the, related alpha and beta, and consider the probability that P alpha and P beta both happen. Here, so again, alpha and beta happen. Then what do we know is that we consider A sub alpha and A sub beta, then they must have common edges. So again, A sub alpha and A sub beta are both set of edges. So they must share some common edge. So these are set of edges, but they occupy the vertices as well, right? They occupy V vertices. So if you consider these as a graph which also has vertices and edges, then they must have at least 2 common vertices, because they must share an edge as a edge set. So let's say for each j at least 2, let f sub j is the maximum number of edges in the intersection of these 2 edge sets, where alpha beta are related and A alpha and A beta as a graph they intersect at j vertices. So for example, if you have, say, C6 as your H, and F2 is obviously, when you have 6 vertices and 6 vertices, and they intersect at 2. And both of them, here we have a H, here we have a H. Then maximum number of edges in the intersection is 1. You cannot have more than 1. But if you have 3 vertices and 3 vertices, then again maximum, you cannot have 3 here because both of them doesn't have triangle. So maximum number of edges you can get here is 2. And also if you have 4, then again maximum possible number of edges is 3. So in this way we can actually, this is what fj mean. Then what do we know? If j is between 2 and v, and alpha and beta are different, then what do we know is this A alpha and A beta is a proper subgraph. H. So when J is V, we could have again, alpha and beta occupy the same vertex. That could happen. In this case, if they all, share the same edge, all 6 edges are same when H is C6, then alpha and beta are same, so that's not the case. Then, so we can actually check that in this case, I draw 7 vertices. In this case, we can actually check that the best case scenario is that they share 4 edges. That's maximum possible. So F6 in this case is 4. So this is a proper subgraph of H. Hence, we know that H is strictly balanced. That implies what? Fj is number of edges in j vertices, which are subgraph of H. Whatever happens in here, so this is a copy of H. So edges here are subgraph of H. That's smaller than E over V. So remember that in C6 case, let's say this is one copy of C6. Let's say this is one copy of C6. Give me a moment. It could happen that this specific case, this does not achieve the maximum Fj, but it could happen that some of the edges, so in here intersection is 1, but there could be other edges which belong to only one. In this case, only this one is contributing to this here. So if we count Fj in this case, we only count this one. But this is not maximum in this specific case, as we can take this, then the Fj has bigger value than before. So, and Fj is the maximum. Anyway, we have this inequality. Now, how many choices of alpha and beta? We want to compute this. So we know that n to the 2b minus j times some constant many choices of alpha beta, where a alpha and a beta are intersecting at j vertices. Because if they intersect at j vertices, then n minus j here, n minus j here. So you choose two, say b minus j, b minus j. You choose two b minus j vertices. And then you have to designate which vertex will play the role of which vertex of H. those are only constant. I mean, some function of b and j and e, which are only constant when n is, I mean, a function that growing. These are just fixing number fixed by h. So also for alpha vector, where this a alpha and a beta intersecting at j vertices, what do we have? The probability that b alpha and b beta both happen is the probability that those edges which lies in the union of a alpha and a beta are all present. And these two are two copies of h. Total, there are 2e many edges, but some edges are overlapped. So this is the number we have to count. As before in the triangle case, instead of, I mean, 3 edges, instead of 6, there is this one intersection. So we want this 5 edges to present to get this 2 bad event. So watch this. This is m mod p to the 2e minus fj. We know that fj is bigger than or equal to this number, so we get this. So what do we know? So delta is, we take j from 2 to b. There are n to the 2b minus j choices of alpha beta, and each term, this is p to the 2e minus f. But what was p? P was n to the minus b over e. So n to the minus b over e times 2e minus f j. So here n to the, you compute it, then 2b plus e over e under b fj. But here e under b fj is bigger than 1 over j. So this with this is n to the, this 2 cancels out, bfj over e minus j. But what do we know? Yeah, let's flip it. bfj over e is smaller than j. So you subtract j, then it is smaller than 0. So this is smaller than 0. So each term is little of 1. And if we add, so this is term goes to 0 as n grows. So this goes to 0 as n grows. So by Janson's inequality, we have that the probability of none of the bad events happen is e to the minus mu plus delta over 2. Here this is little of 1. And this mu is again this. And this is lower bound. So we know that this is e to the negative c square over c to the e over a plus little of 1. So this proves this theorem. Now we have this. So in the next video, let's prove one more Janson's inequality. Yeah, one more Janson's inequality.